You click Enter. In less than a second, the system validates the request, checks the password, creates a session, queries the database, writes a log, and returns a response. It looks like one simple call. But behind that click, there's an entire backend making decisions. And almost every production-grade backend relies on the same 10 ideas. Regardless of language or framework, these concepts show up in any real system. Tutorials teach you the happy path, the request that works, the query that returns fast, the login that just succeeds. They almost never teach you what happens when the money's wrong, the cache is stale, or the queue is on fire. That's exactly the gap this video closes, one concept at a time, counting down from the most surface level to the one that ties everything else together. Number 10. Request and response. Every backend starts with a message arriving. A client requests something, the server processes it, and a response comes back. Sounds obvious, but it's the foundation of almost everything. A request typically has a method, get to read, post to create, put or patch to update, delete to remove, a route, like /API/orders, headers carrying metadata like the auth token or content type, and sometimes a body, the actual payload. The response has structure too. The status code tells you what happened. 200 means it worked, 401 means authentication failed, 404 means it wasn't found, 500 means the server broke. Request and response are the basic grammar of backend communication. But for two sides to actually understand each other, they need to agree on the shape of these messages. Number 9. The API contract. An API is a contract between the caller and the provider. The frontend shouldn't need to know how your database table is structured, or which framework the server runs on. It just needs to know which route to call, what data to send, and what response to expect. That's what lets the backend change internally without breaking anyone. You can swap databases, split a service, rewrite the internal logic. If the contract stays stable, every client keeps working. A well-written contract also states clearly what's optional, what's required, and how the system behaves when something goes wrong. But before running any business logic, the backend has to decide if the incoming message even makes sense. Number 8. Validation and business rules. The backend can never trust what comes in from outside. If the quantity is negative, it shouldn't pass. If the field claiming to be an email isn't one, it shouldn't pass. If the price came from the client, the backend often has to ignore it and recalculate from its own source of truth. This exists to protect the system's actual rules. A common way to organize it is in layers. A controller that understands HTTP, a service that understands business logic, and a database that just stores data. That separation keeps critical rules from being scattered across the codebase. And once a rule starts appearing in 5 different places, the system starts contradicting itself. Once the backend has validated what a request is trying to do, the next question is obvious. Who's asking? Number 7. Authentication and authorization. These are two different things. Authentication answers who you are. Authorization answers what you're allowed to do. You can be fully logged in and still not have permission to refund someone else's payment. In practice, the backend usually receives some kind of credential, a session cookie or a JWT, that proves the request came from someone known, and separately checks whether that someone has permission for that specific resource. A lot of real security incidents come from a system that checks one of these and quietly assumes the other. Knowing who's asking and what they're allowed to do still doesn't answer the most important question. Where does the data actually live? Number 6. Database and modeling. Storing data means deciding how the real world translates into your backend structure. An order has a user, line items, a payment method, an address, a status. Model it poorly, and your business rules get confusing fast. Overnormalize, and a single query can turn into 5 joins. Performance lives here too. A naive query can turn into a full table scan, while the right index finds the same row in a handful of steps. So when something in production gets slow, one of the first places to look is whether there's a missing index, or a table structure that forces the database to read from 5 places instead of 1. But a database isn't only for storing data, it also has to keep that data correct while multiple things happen to it at once. Number 5. Transactions and consistency. Picture a transfer. Withdrawing $100 from one account and depositing it into another are 2 separate operations. But for the system, they have to behave as one. Either both happen, or neither does. That's what a transaction guarantees. a kind of isolation where everything inside it commits together or fails together. Without it, a network blip, a bug, or a crashed process can leave the system in a state that never should have existed. Consistency also has to survive competition. Imagine two people buying the last unit of the same product at the same instant. Both read a stock count of 1. Both try to confirm. If the backend doesn't protect that critical section, it sells something it doesn't have. Consistency has a cost though, and when that cost becomes latency, a lot of systems reach for the next concept. Number 4. Cache. Caching means keeping a copy of an answer close to where it'll be needed again, so you don't recompute it or hit the database every single time. When the data is already in the cache, that's a cache hit, fast response. When it's not, that's a cache miss. The system fetches the real data, saves a copy, and serves that copy next time. But cache has a real problem. If the underlying data changes, the copy can go stale, and stale data causes real bugs depending on your domain. Caching speeds up reads, but it raises a harder question. When does this answer stop being true? A well-built backend doesn't cache just because it's fast. It also has a plan for when and how to invalidate. Not everything, though, needs to happen the instant the request arrives. Number 3. Queues and workers. Not everything has to finish while the user is waiting. If someone completes a checkout, the system needs to respond fast, but sending the confirmation email and generating the invoice don't need to block that response. Queues separate the request from the heavier processing. The API drops a message, and a worker picks it up later. More jobs, longer queue. Need it faster, add more workers. But queues bring their own problems. What if the job fails? What if it runs twice? What if the queue grows faster than the workers can consume it? That's why using queues means thinking about retries, idempotency, ordering, and monitoring from day one. And once all of this starts to actually grow, the next concept shows up on its own. Number 2. Scale and availability. Scalability is whether the system keeps responding as volume increases. At first, one server usually handles everything. It takes the request, runs the logic, queries the database, returns the response. But as the product grows, that same server starts seeing more users, more API calls, more database queries, more background jobs, more sudden spikes. At real scale, the question isn't just does the code still work, it's what happens when 1,000 people show up at once. Availability is a separate concern. The system has to keep running even when something fails. There are 2 basic paths: scale vertically, a bigger machine with more CPU and memory, or scale horizontally, more machines splitting the traffic. Horizontal is more common in modern systems, but it demands something extra. If each server only keeps state in its own memory, a user can land on a different instance and lose all context. A session that exists on machine A doesn't exist on machine B. That's why many backends aim to be stateless. The important state lives somewhere shared, like Redis, a cache layer, or an external store, so any instance can answer the next request. Availability also depends on knowing which parts of the system are actually healthy: load balancers, gradual rollouts, rollback, redundancy. A load balancer shouldn't send traffic to an instance that's already down. A deployment shouldn't take every machine offline at once. Scaling isn't just adding servers. It's designing the backend to distribute load even while something somewhere is failing. And to know when something has failed, you need to be able to see inside the system. Number 1. Observability. Observability is the ability to understand what's happening inside a system by reading the signals it emits. When the backend breaks, what's throwing an error isn't enough. You need to know which route failed, at what time for which user, after which deployment, and at what exact point in the flow things slowed down or stopped. Without that, you don't even know where to start looking. The 3 most common signals are logs, metrics, and traces. Logs describe specific events: a request came in, a validation failed, a payment was declined, a worker processed a job. Metrics describe behavior over time: error rate, latency, CPU usage, queue size, requests per minute. Traces follow a single request's actual path through the system: API, then auth, then the service layer, then cache, then the database. And if the database step alone took 800 milliseconds, the trace makes that visible immediately. Each signal answers a different question. Logs tell you what happened, metrics tell you if the problem is growing, traces tell you exactly where the time went. And that's the thing about observability. It doesn't replace databases, caches, queues, or authentication. It's what ties every one of those 9 concepts together in the real world. You can build a backend without it. You can't reliably keep one alive without it. None of these 10 ideas are exotic. Every one of them shows up in the first few weeks of a real production job, and almost none of them show up in a beginner tutorial, because a tutorial's job is to get you to it works, not to keep it working under load, under attack, or under a bad deploy at 2 a.m. If you want to see exactly what happens when concept number 5, consistency, collides with concept number 2, availability, at real scale, across 2 data centers on 2 different continents, that's the entire subject of the computer dilemma on this channel. It's the trade-off every distributed system eventually has to make, whether anyone on the team ever named it out loud or not.